G'day everyone. In this video we're going to be covering the definite integral. In this case I've just called it J, which is the integral from 0 to pi over 2 of cos of tan of x dx. And in this approach we're going to be appealing to the standard ones, the standard theorems and rules that we tend to in the videos that I do. So dominated convergence, well, essentially a combination of Feynman's trick, which requires the dominated convergence theorem. We're going to use a basic U substitution. Then we're also going to apply Fubini's theorem with Laplace transforms in order to be able to resolve this. Now, on the surface, it actually looks quite nicely cos of tan of x. We've got a function of a function. But it actually turns out to be a rather simple integral to evaluate. Okay, so the first thing that I wanted to do was, I saw I had tan of x here, and I had 0 and I had pi over 2 here. And so my first thought was, well, if I utilize tan of x as a substitution, i.e. u equals tan of x, then I'm going to get an upper bound of infinity because of tan of pi over 2, which is a limit that goes to infinity, and tan of 0, which would be 0. I also know that through the derivative, I'm going to end up with something of x squared or u squared plus 1 over the bottom. So that just wanted you to let you know, and that's what we do within the next step. Well, we first define a function, sorry. Just wanted to give you a background of what motivates my steps as I go along. I apologize, I've gotten out of order a little bit. So here we are utilizing Feynman's trick, and we're going to define a new function f of t, which is the integral from 0 to pi over 2 of cos of t tan of x dx. In this case, I've defined t in this case to be a real value, and I've defined it to be greater than 0. Just so you're aware, we could actually have t being less than 0. So cos of negative t, because t is an even function, that would just be equal to cos of t. So this restriction here need not be imposed as it being positive, because it would already come out with that. But if we force it or have it as like the absolute value of t, then what is good about this is that the dominated convergence theorem, which is required to utilize the methods that I'm about to use, is satisfied. We also see that our integral here, j, is just this function evaluated at t is equal to 1. So fairly simple stuff. Okay, so as I was saying before, the substitution that I wanted to do first was to try and get rid of the tan from inside of here, and I knew that through the derivative it was going to put it over u squared plus something, and there'd be a 0 to infinity. So, don't beat yourself up if you're watching this for the first time and you go, well, how did he know that? I've been doing these for a long time, and you pick up on the patterns. So if we let u equal tan of x, then du dx is just equal to sec squared of x, which is equal to tan squared plus 1, which therefore, because u is equal to tan squared, is equal to u squared plus 1. So therefore, rearranging it into the form of dx, so just bringing it up and then dividing this through down to here, we have dx is equal to du over u squared plus 1. So that's what we're going to have replaced here. This is going to become cos of tu, and then the bounds change from being, so at x equals 0, we have u is equal to tan of 0, which is 0. And at x is equal to pi over 2, we have u is equal to tan of pi over 2. It's discontinuous at pi over 2, but it approaches positive. And so therefore, the integral that we have, f of t, which is equal to the integral from 0 to pi over 2 of cos of t tan of x dx is equal to the integral 0 to infinity. As I said, we just transformed the bounds here. Cos of t u, so we have replaced the tan of x with u. And the dx, which we reformed here, now becomes 1 over u squared plus 1 du. So we have the integral from 0 to infinity of cos of tu over u squared plus 1. I can't remember if I've covered that in a separate video, but essentially we're also going to cover that now here. So we have two integrals that we're able to cover, which is great. Okay. So the next step is I'm going to take the Laplace transform, and the reason why I want to take the Laplace transform is, first of all, I know in order to take the Laplace transform of the integrand, or of the integral which becomes the integral of the Laplace transform, we need to apply to Fubini's theorem, and that is satisfied in this case. So the beautiful thing about that is the Laplace transform of cos of tu transforms it into a form of a over s squared plus, s over s squared plus a squared. So it converts it from being a cos term into an algebraic term that has the exact same composition as what we have in the denominator. So it'll be u squared plus something. So that's beautiful. So that means that we end up with a product of two of these, and then we can separate them out using a partial fraction decomposition, evaluate them individually, and then take the inverse Laplace transform, and we're done. And so that's all we have here. The Laplace transform of f of t is equal to the Laplace transform of the integral. Now, through Fubini's theorem, the Laplace transform of the integral becomes the integral of the Laplace transform, which is what we have here. Now remember, anything that isn't t, because we're taking the Laplace transform with respect to t, anything that isn't t we can just bring out the front, which is essentially what I've done here. This becomes the Laplace transform of cos of tu over u squared plus 1. So I've just sort of put it in a different form. Okay. So the Laplace transform of tu is just equal to s over s squared plus u squared. So just look it up on your Laplace transform table. I've said this in other videos. If people would like to see a derivation of that, please let me know in the comments or send me a direct message and I'll do a video for that. And then the leftover term is just this 1 over u squared plus 1, which is what we have here. Now, as I said before, we've taken it from, as I said before, we have taken it from this form and we've been able to convert it into two algebraic forms where they have the exact same structure and they're both really easy to integrate. So that's beautiful. And so what we can do with the combined of them being multiplied is we can just apply a partial fraction decomposition, which is what I've done here, to take it from the product state that it's currently in and put it into a sum of individual states, which is what we have here. Again, I'm assuming that if you're doing integrals of this nature, you probably know partial fraction decomposition back to front. However, if not, please, again, let me know in the comments or send me a direct message and I'll do up a video to show you how to do that. It's a very important tool to have within your toolkit when it comes to approaching integrals, at least with the sort of integrals that I work on, and it's a magnificent tool because, as I said, it takes products, puts them into sums, and then in general that makes them much easier to evaluate. So we have s over s squared plus 1, 1 over u squared plus 1 minus 1 over u squared plus s squared du. Now remember, this is an integral with respect to u, so this s term can go out the front. And so if we integrate the first term, that just becomes arctan of u. If we integrate the second term, that just becomes 1 over s arctan of u over s. If you're unsure, in both cases, just let u equal tan theta and it comes out very easily. Okay. So now what we're going to do is we're going to apply the limits. Remember that in a Laplace transform, s is actually a complex value whereby its magnitude is greater than 0. So when we have 1 over s here, we know that this is a positive quantity. That is very important because when we apply infinity, it doesn't matter with 0 because 0 multiplied by anything is going to make it 0. But with infinity, if it's a positive, it's positive infinity. If it's a negative infinity, if it's a negative infinity, if it's a negative. So that's why it's very important to know here that s is a positive quantity. Now arctan of infinity is just equal to pi over 2. So we have pi over 2 here minus 1 over s pi over 2, which is what we have here. And then for the lower limit, I haven't included it, but arctan of 0 is just equal to 0. So we have 0 here and 0 here, so it's completely cancel out. There's nothing there. And so as I said, what we're left with is this upper bound term or evaluation. In the next step, what I'm going to do is I've done multiple steps here. Excuse me. I'm going to draw the pi over 2 out the front, which is what I've got here. We're going to combine this over, combine the two fractions that we have here, which is 1 minus 1 over s. And we can see here that that just becomes s minus 1 over s. Very easy to do. And then what was left over is this s over s squared minus 1, which is what we have here. Now, s squared minus 1 is just completing the squares. S minus 1 times by s plus 1. So we have s minus 1, s plus 1, and so the s minus 1 cancels with the s minus 1 on the bottom here, and what we're left with is s plus 1 here. This s obviously just cancels out with this s, and so then they're gone, and so we're left with 1 over s plus 1, and then just the leftover term here of pi over 2. So now we have got our expression for the Laplace transform of the integral, and so now in order to resolve the integral we need to take the inverse Laplace transform, and thankfully it's in a very simple form. So I of t, my apologies, this should be lowercase f and same down here. F of t is equal to the Laplace, inverse Laplace transform, of the result, which we have here, 1 over s plus 1 pi over 2. Remember, we're taking the inverse Laplace transform with respect to s, so this pi over 2 is just a constant, which can be drawn out the front. And we have the Laplace inverse of 1 over s plus 1. This is a very common and easy one. Laplace transform of 1 over s plus a is e to the negative at. So here in this case, our a value is just equal to negative 1. And so we have pi over 2 e to the negative t. Again, if you would like to see a derivation of that, comment or send me a direct message and I'll do a video to support that. So we now have the solution to our more complicated expression, which we should we have two integrals here. I mean, it's the same integral repositioned in two different ways, but the integral from 0 to pi over 2 of cos of t tan of x dx is equal to pi over 2 e to the negative t, and equally, the integral from 0 to infinity of cos of t u over u squared plus 1 is equal to pi over 2 e to the negative t. So again, I mean, look, it's a simple transformation. All I did was let u equal tan of x, my apologies, in order to get it. These are telling the same story, but sometimes, it's not so intuitive, and that's why it's important at the beginning to go, okay, I see this tan of x, and I see these two limits. It's going to transform it into something that I'm also familiar with. Okay. Now, we do know specifically here, though, that for our integral j, it is evaluating f of t when t is equal to 1. Again, my apologies, there should be lowercase f here. So we know here that f of j, is equal to f of 1, which equals pi over 2 e to the negative 1, just evaluating at t is equal to 1, which is just equal to pi over 2 e to the negative 1, which is what we have here, which is another way of expressing it is obviously just pi over 2e. And so therefore, bringing it all together, the integral from 0 to pi over 2 cos of tan of x dx is equal to pi over 2e. Okay, so that's all we have in this video. If you like the video, please like it. If you would like to see more videos of this nature, please subscribe. As I say in all my other videos, if you have any suggestions or any requests or any critiques, please comment or send me a direct message. If it is a request for an integral you would like to see covered, please let me know. I try to cover them whenever I can. So if you send one through, if I am able to solve it, I will definitely solve it and I'll put a video together. Otherwise, I look forward to seeing you in the next video. Okay, thank you. Bye.